Okay, so this video is going to cover exponential functions, and let's look at what these are. What they are is where your x is going to be in the exponent spot. All right, and we don't want a to be 1 because 1 to any power is 1, and we have to be careful of 0 to the 0, and we have to be careful of it being of where our negatives are and different things. But let's look at my first example here. What if I have f of x and it equals 3 to the x power? Okay, so let's look at what the graph would look like when we have something like this. So here's our x and our y. Let's put in some values. So let's put in 0. 3 to the 0. Remember, anything to the 0 is 1. Let's put in 1. 3 to the first power is 3. Let's put in 2. 3 to the second power is 9. And we'll put in 3 and we get out, what, 27. And then let's put in a couple negatives because 3 to the third is 27. Let's put in like a -1. Well, 3 to the -1, remember that's like flipping it and it becomes a third. Okay, so when you take something to a negative power, it's going to get really small really fast. And so let's kind of look at overall what the exponential graphs look like. So 0, 1 is going to be here, and then we have 1, 3 here, and then 2 goes up to 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9, way higher than I drew. Okay, so it looks like that, and then at -1 we were at a third, so it's going to be about here. If we were at -2, we would be at 1/9, so it'd even be smaller, and you get smaller and smaller, but you can't ever actually be on that axis because the numbers just are fractions, right? And they get smaller and smaller and smaller. So it kind of gets really close here on the graph. Oops, I missed my dots. And then it's going to go up like this. And that's, you know, a pretty common looking graph of an exponential. You can move these all around and shift them in all sorts of ways. The 3 changes the power in which it goes up. You know, we can look at a 2 and it would go up a little bit slower. If we could look at a 5, it's going to go up even faster, and so forth. So this is our basic idea. And if I change and I have a negative in the exponent, I'd flip my direction going the other way. And let's see. Then we start to look at equations, and the equations are a little bit harder. So the graph is this basic graph here. So let's look at a couple equations though, because these are a little bit harder. What if I say 6 to what power is equal to 36? Okay, so pretty basic. 6 to what power is 36? Well, we can think of it as 6 to the x equals, well, let's rewrite this is the same base as here. So we have the same base. Most of you probably just went 2. Why did you do this? But this idea of writing them as the same base will help you solve the really complicated ones. So we can see that x has to equal 2 because we can, once we have the same base, we can set our exponents equal to each other. So x is 2. Let's look at 1. That's way harder, so but similar idea. So I have 9 to the 2x minus 8 is going to equal 27 to the x minus 4. Okay, so right now we have 9 and 27. Those are not the same, but both of those can be written in the powers of 3. Okay, so think of this one, and it might be helpful to like write out a chart of all the powers. It's just nice to have them. You can do them really fast on Excel. But we can think of this one as 3 squared, right? But then if I move that up here, then I have to times it by what's already up there. Same idea here. 3 to the third power is 27, so I'd become 3 to the third, but then you already have that x minus 4 up there. So then now we have the same base, so we can set this equal to this and solve. So we have 2x minus 8 equals 3 times x minus 4, and then we need to distribute, so we get 4x minus 2 times 8 is 16, 3x minus 12. Subtract the 3x over, so you get your x's together to give you 1x. Add your 16 this way, and you get -12 plus 16 and you would get 4. So even if they're harder like this one, you can set the bases to be the same and still be able to solve that type of equation. We'll learn in this section, as we start doing more and more logs, you'll learn another way to do this type of problem with the x as the exponent. So let's look at one more because it's a fraction and it's a little bit confusing. Oops, this is my fourth one. What if I have 3 halves all to the x power equals 8/27? Okay, so 3 halves to the what power is going to equal 8/27. So what I really want to do is I want to think of rewriting both 8 and 27 with exponents so that they both have the same power kind of idea. So bear with me, you could just play with them a little bit. I thought, okay, well, 8 is 2 to the third and 27 is 3 to the third. And I thought, well, wow, look, 2, 3, 3, 2. Similar, but yet different because one's in the denominator, one's on the numerator. Remember, to flip that, that's a negative exponent idea. So I'm thinking of this as, let me move it over here. I'm thinking of it as this 3 halves to the x. I'm going to write it as 2/3 to the 3, which we're getting super close, but then we want to flip these. So I'm going to change that to a negative. And oops, and I didn't flip them. And that becomes 3 halves. Now we have the same numerator denominator, and we can set these equal, and so you can see that x is equal to the -3. So if it's a flipped over, you're going to have a negative in the exponent place, and that's a little bit tricky. So again, the basic graph kind of looks like this up here, and you're going to flip it around, do different translations and transformations, just rotating it around depending on what numbers you have here, and if you have numbers up here, and if you add numbers outside and that kind of thing. Just like anything else that we graph, you have a parent graph, and then you change it around depending on the numbers. Okay, so that's an overview of 10^2 or just exponentials.